Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the vapor compression refrigeration. It is well known that the reversed color cycle is the most efficient refrigeration cycle operating between TL and TH. However, it's not a suitable model for refrigeration cycles since process 2 to 3 and 4 to 1 are not practical because process 2 to 3 involves the compression of a liquid-vapor mixture, which requires a compressor that will handle two phases, and process 4 to 1 involves the expansion of high moisture content refrigerant in the turbine. For the reverse color cycle, we have COPs for refrigeration and heat pump. Both COPs increases as the difference between the two temperatures decreases, that is, as TL rises or TH falls. Even though the reverse color cycle is not practical, it can serve as a standard against which actual refrigeration cycles are compared. Let's firstly talk about the ideal vapor compression refrigeration cycle. Many of the impracticalities associated with the reversed color cycle can be eliminated by vaporizing the refrigerant completely before it is compressed and by replacing the turbine with a throttling device, such as an expansion valve or capillary tube. The cycle that results is called the ideal vapor compression refrigeration cycle, and it is shown schematically and on a TS diagram in figures 12.10 and 12.11. The vapor compression refrigeration cycle consists of four processes. 1. Process 1 to 2 is the isentropic compression in a compressor. 2. Process 2 to 3 is the constant pressure heat rejection in a condenser. 3. Process 3 to 4 is the throttling in an expansion device, and 4. Process 4 to 1 is the constant pressure heat absorption in an evaporator. The vapor compression refrigeration cycle is the most widely used cycle for refrigerators, air conditioning systems, and heat pumps. In an ideal vapor compression refrigeration cycle, the refrigerant enters the compressor at state 1 as saturated vapor and is compressed isentropically to the condenser pressure. The temperature of the refrigerant increases during this isentropic compression process to well above the temperature of the surrounding medium. The refrigerant then enters the condenser as superheated vapor at state 2 and leaves as saturated liquid at state 3 as a result of heat rejection to the surroundings. The temperature of the refrigerant at this state is still above the temperature of the surroundings. The saturated liquid refrigerant at state 3 is throttled to the evaporator pressure by passing it through an expansion valve or capillary tube. The temperature of the refrigerant drops below the temperature of the refrigerated space during this process. The refrigerant enters the evaporator at state 4 as a lower quality saturated mixture, and it completely evaporates by absorbing the heat from the refrigerated space. The refrigerant leaves the evaporator as saturated vapor and re-enters the compressor, completing the cycle. Notice that, unlike the ideal cycles discussed before, the ideal vapor compression refrigeration cycle is not an internally reversible cycle, since it involves an irreversible process. This process is maintained in the cycle to make it a more realistic model for the actual vapor compression refrigeration cycle. If the throttling device were replaced by an isentropic turbine, the refrigerant would enter the evaporator at state 4' instead of state 4. As a result, the refrigeration capacity would increase, and the network input would decrease. Replacing the expansion valve with a turbine is not practical, however, since the added benefits cannot justify the added cost and complexity. In a household refrigerator, the tubes in the freezer compartment where heat is absorbed by the refrigerant serves as the evaporator. The coils behind the refrigerator where heat is dissipated to the kitchen air serve as the condenser, as shown in the figure. Another diagram often used in the analysis of vapor compression refrigeration cycles is the pH diagram, as shown in figure 12.12. On this diagram, 3 of the 4 processes appear as straight lines, and the heat transfer in the condenser and the evaporator is proportional to the lengths of the corresponding process curves. All 4 components associated with the vapor compression refrigeration cycle are steady flow devices, and thus all 4 processes that make up the cycle can be analyzed as steady flow process. The kinetic and potential energy changes of the refrigerant are usually small relative to their work and heat transfer terms, and therefore they can be neglected. Then the steady flow energy equation on a unit mass basis reduces to the condenser and the evaporator do not involve any work, and the compressor can be approximated as adiabatic. Then the COPs of refrigerators and heat pumps operating on the vapor compression refrigeration cycle can be expressed as. Now let's talk about the actual vapor compression refrigeration cycle. An actual vapor compression refrigeration cycle differs from the ideal one in several ways, owing mostly to the irreversibilities that occur in various components, mainly due to fluid friction and heat transfer to or from the surroundings. The COP decreases as a result of irreversibilities. The TS diagram of an actual vapor compression refrigeration cycle is shown in the figure. An actual vapor compression refrigeration cycle is different with an ideal vapor compression refrigeration cycle as follows. The compression process is non-isentropic compression. The vapor and evaporator exit is not saturated vapor instead of the superheated vapor. The liquid and condenser exit is not saturated liquid instead of the subcooled liquid. There are pressure drops in both condenser and evaporator. Okay, that's all for this task. Thank you very much and see you next time.